Okay, the next topic is linear algebra. I assume that you guys have at least basic understanding of some basic things of linear algebra, such as vectors and matrices and operations such as transpose and so on. So let's go fast on those things. Vector is a collection of numbers. So we use this notation to denote a vector. Depending on how many numbers in this collection, we call dimension. We call n dimension. So if you have two numbers in the notation, you have two-dimensional vectors. If you have three numbers, you have three-dimensional vectors, and so on. We are going to talk about real vectors, meaning that the element in this vector is every element in this vector is real number. Depending on how you present your collection of numbers, your vector can be a column vector or row vector. Column vector is a vector that has numbers in a column way, in the vertical way. Row vector is a vector that has numbers in a horizontal way. In econometrics, we are dealing with column vectors. So unless otherwise specified, a vector means a column vector. We are going to use special vectors and matrices. For example, here, this notation, 0 subscript n is an n-dimensional zero vector. So it's the origin of n-dimensional Euclidean space. So 0 subscript 2, for example, is 0, 0. 0 subscript 0 subscript 3 is 0, 0, 0. Okay. If the dimension is obvious and the fact that this 0 is a vector, we can just use 0. So 0, depending on the context, may mean a numerical value 0, scalar 0, or a 0 vector, an n-dimensional 0 vector. This one is called transpose. So 0, 2-dimensional, 3-dimensional 0 vector, 0 sub 3 is 0, 0, 0. When you transpose, it's gonna be 0, 0, 0. Okay. This notation here is a Greek letter iota. Iota super subscript n, iota n, is an n-dimensional vector with 1. So you have 1, 1, 1, and so on. Okay. So iota prime, therefore, is a row vector of 1s. Okay. All right. So iota 3 prime 1, 2, 3 means 1 plus 2 plus 3, right? Here are some basic operations. Transpose, we already mentioned. Scalar vector multiplication. So if you multiply 3 to 1, 2, 3 vector, it means that 3, 6, 9. So in terms of graphical representation, let's think about this vector 1, 2. 1, 2 is a point in the two-dimensional Euclidean space. Here's 1, here's 2. Right? So this point is a vector 1, 2. So when you multiply 2 to this vector, it goes here. And 2, 4. Okay. So scalar multiplication is the extension, in a sense, or shrinkage of a vector. Okay, you can add two vectors. So addition of, say, 1, 2, and 3, 4 is 1, 2. Say this is 1, this is 1, this is 2. So this vector is 1 and 2. And this is 3, and this is 4. This vector is 3 and 4. So if you add these two, you get 4, 6. And graphically, 4, 6 means, so let's just exaggerate the graphs. So suppose this is your 1, 2, and this is your 3, 4. Then 1, 2 plus 3, 4 is you bring either this vector to here, or this vector to here, and the points that the end point of the new vector indicates is the summation of these two. So this is your 1, 1, 2. This is your 3, 4. Then this point is your 4, 6. Okay. That's how you add vectors. So vector addition is element-wise addition, and it means graphically or geometrically this new vector point. Okay, you can add the same dimensional vectors only. So for example, this and these two vectors are not addable. There's inner product. Inner product of two vectors is this. So here A, B, inner product or dot product C, D is A, C plus B, D. So inner product is a vector and vector to a scalar operation. Okay. Sometimes inner product may be this notation may be used for inner product, and by definition, inner product of U and V vector is multiplication of U transpose V. Okay. There's this outer product. We probably won't use the outer product quite often, so let's just skip this. Norm means the length of a vector. Length, if you do not have any other restriction, a norm or length is a two-dimensional Euclidean length, or just Euclidean length. Euclidean length is this. So a vector here, this is A, B. the Euclidean length of this vector is, by the Pythagorean theorem, is square root of a squared plus b squared. So it's like AB inner product AB square root, right? So here this is a typo. So we use this notation to denote an inner product. So AB double vertical line bracket means the length of a vector, or norm of a vector. It means that here, like this, it means that AB inner product AB square root. Okay, like this. Norm is not just square root of this one. Norm can be defined in a various ways. So we use P norm. P norm means the notation for a P norm is this. Okay, so the norm notation, usual norm notation with P here, P is greater than or equal to 1 usually, and the definition of P norm is this. Okay, so for example, if P is 1, is called the taxicab norm, or just one norm is here. I skipped the omitted the absolute value here. So the norm here is this just sum of these three. So if you have -1 and 1, the norm, one norm is 1 plus 1, which is 2. Okay. When P is infinity, it's called the sup norm. Sup norm means the maximum value of your element. Okay, like this. So in this notation, our Euclidean norm here is more properly called by 2 norm, right? 2, but often we omit the 2. Okay. A unit vector is a vector whose norm is 1. So any vector can be normalized by dividing itself by its norm, right? So 1 and 2, the length of this is square root 1 plus 4, which is square root 5. So if you divide this whole, every element, each element by square root of 5, one over square root 5 and 1 over square root 2 over square root 5. This new vector is a unit vector. You can visualize that every point in this circle with radius 1 is a unit vector, right? So this is a unit vector, this is a unit vector, this is a unit vector, and so on. And you can extend this concept to 3-dimensional, 4-dimensional, even higher dimensional Euclidean space. A matrix has 2 dimensions, one row dimension and the other column dimension. Row dimension, matrix is this, right? Matrix is this. In this case, how many rows does this matrix gives you the row dimension? In this case, n, and there are m columns in this matrix. It's called the column dimension. So n by m dimensional matrix can be written this way. Okay, I'm gonna use this notation, and this notation is by no means universally accepted. Okay, so this is basically for my course only, for the simplification of notations. A transpose. Okay. Now think about the system of equations. So here, if you are not familiar with this many variables, just use two variables or three variables, like 3x plus 2y plus 4z is 3, 4x minus y plus 2x is 4, and x plus y minus 3x is 6. Okay, and if you use the matrix rule, you can rewrite this system of equations by using a matrix, 3 coefficient matrix, 3, 2, 4, 4 minus 1, 2, 1, 1 minus 1, and variable vector x, y, z, and a constant vector 3, 4, 6. Okay, so this, when you write this matrix notation and this system of linear equations mean the same thing. Often we are going to use a boldface capital letter to denote a matrix. So in this case, let's call this XA, and we are going to use lowercase letters to denote the vectors. So let's call this X and this B. So we may write the same the system of equations A x equals B. Okay. You can transpose a matrix. When you transpose n by m matrix, it gives you m by n matrix. Okay. You can multiply a scalar to matrix. So if you multiply 3 to 1, 2, 3, 4, 5, 6, it gives you 3, 6, 9, 12, 15, 18. Okay. You can add two matrices. One, two, 3, 4, 5, 6 plus 1, 2, 4, 3, 6, 9 gives you is element-wise addition. Is 2, 4, 7 and 7, 11, 15. Okay, you can multiply two matrices. A matrix multiplication is a bit complicated, so I want you to practice these operations. Okay. There's a convenient mathematical operation which is called a Kroneker's product. So matrix multiplication cannot be done with it has some restrictions on the dimensionalities of matrices. So for two matrices A and B to be multiplicable, the column dimension of A and row dimension of B must be the same. When you do the Kroneker's product, it doesn't really matter. Okay, so Kroneker's product is like this. We use this circle product notation to denote a Kroneker's product usually. So when you Kronecker multi-product, Kronecker product 1, 2, 3, 4, 1, 2, it gives you 1 times 1, 2, so 1, 2, and 3 times 1, 2, so 3, 6, and 2 times 1, 2, 2, 4, and 4 times 1, 2, so 4, 8. Okay, that's how you do the Kroneker's product. There are rules that the Kroneker's product must obey. These rules. Okay, so get familiarized with them. We are going to use identical matrix. Identical matrix is a matrix of zeros and ones where the diagonal elements are zeros and all off diagonal elements are ones. So for example, I with 2 is two-dimensional identity matrix, which is 1, 0, 0, 1. Okay, you can see that when you multiply a matrix to identity matrix, it gives you identity matrix and the matrix A, which is itself. Okay, inverse matrix. So an inverse matrix is denoted by A inverse minus 1 to the power minus 1 and is called the inverse. Inverse matrix is a matrix that pre-multiplication to a matrix and post-multiplication to matrix gives you the identity matrix. Not every matrix has an inverse matrix, but if it does, it's unique. Okay. When a matrix has an inverse matrix, it's called invertible. When A and B are invertible, then A times B inverse is B inverse times A inverse, and A transpose inverse is A inverse transpose. Okay. Square matrix is a matrix whose column dimension and row dimensions are the same. Idempotent matrix is when you multiply itself, it gives you the same matrix. Okay, an identity matrix is idempotent. Okay, so an identity matrix is idempotent, but an idempotent matrix is not necessarily an identity matrix. So find out an idempotent matrix, a 2 by 2 dimensional, okay, A, B, C, D, and find out this element A, B, C, D such that this. Okay, so it's a practice question problem. A symmetric matrix is a matrix whose transpose is itself. So M prime equals to M. Upper triangular and lower triangular matrix is a matrix whose diagonal, one of the diagonals is 0. So here, if a matrix is 1, 0, 0, 1, 2, 0, 3, 4, 3, it's a lower triangular matrix. A transpose of lower triangular matrix is the upper triangular matrix. A diagonal matrix, I'm going to use this notation here, is a matrix whose off diagonals are 0. For example, 1, 2, 3, 0, 0, 0, 0, 0, 0 is a diagonal matrix. So a diagonal matrix has an important property. So if it has an inverse, then we know what it is. It's the reciprocal, diagonal of reciprocal. So the inverse of this function, this matrix, is 1, 1/2, 1/3. Okay. I'm going to use this notation, e to the power a. E to the power a is just a notation. It doesn't mean anything. Okay. It's just a notation. So exponential of every element is this. It's actually matrix. It's a matrix exponentiation and matrix logarithm are rigorously defined. So when you when you study these things, matrix exponentiation and matrix logarithm, you can see that the rigorous definition of your matrix exponentiation and matrix logarithm are not this. So for the lecture, the econometrics lecture, I'm going to use them without any mathematical meanings. Okay, it's just a notation. This is a matrix. Okay, this is a matrix. So a to the power 1/2. So all these three, okay, and this one, all these three are notations for the specific form of matrices. So e to the power a is when a is matrix a is 1/2 1 2 0 0 1. Okay, then e to the power a means e to the power 2 0, e to the power 0, e to the power 0, e to the power 1. Okay, it's just a notation for this matrix. Log of let's put here. So 1 1 1 1. Log of a means log of 2, log of 1, log of 1, log of 1. By the way, log throughout the course is always natural log. And a to 1/2 means a to 1/2 means is a matrix such that a 1/2 times a 1/2 is 2 1 1 1. Okay, so a to the 1/2 is a b c d. If you write a to the 1/2 this way, it means you need to find out a b c d by solving the following equation: a b c d is 2 1 1 1. Okay, all right. Actually, if your matrix is diagonal, then a 1/2 is quite easy to find. Let's say suppose your A matrix is 2 0 0 1. then a1/2 is simply square root 2, 0, 0, 1, right? But if a is not diagonal, it's not easy to find. This notation here is it means an indicator function. So I may use 1a or IA. Okay. So 1 may be used to denote an indicator function, or it may be used to denote a matrix of 1. So vector 1s, I'm going to be consistent. I'm going to try to be consistent, but I may lose track of my notation sometimes. Okay. So 1a means it's a function. So indicator function is it has two values. It's either 1 or 0. And when does this become 1? If a is true. If a is false. For example, your y is 1, x greater than 2. Then the graph of y is this. Here's 2. Here's x. This is the graph of y. This is your y. Okay. In matrix is called there's a very important operation called determinant. Determinant maps a matrix to a scalar value. A square matrix to a scalar value. Okay. So determinant is defined only to square matrices. Okay. A square matrix A is invertible. When a matrix is invertible, it's called non-singular. If and only if the determinant of A is not 0. So in other words, if the determinant of A is 0, then it's not invertible, it's singular. There are some things that you might want to know about determinant function. For example, determinant of identity matrix is 1. Determinant of A is determinant A of a transpose, so it's transpose invariant. If you change element, this is a matrix. So A1 is a column vector. A1 is a column vector. AJ is a column vector, and so on. So if you permute a column vector, the determinant becomes negative. Okay, so if originally this one is negative minus determinant, then this new permuted matrix determinant is positive. The value doesn't change, the sign changes. Here, if you combine two column vectors and generate a new matrix, the determinant doesn't change. So linear transformation invariant, linear combination invariant. Determinant of A times B, if A times B is possible, is determinant A times determinant B, and determinant of A inverse is 1 over the reciprocal of determinant of A. Okay. Read this part carefully and understand what the determinant implies in terms of geometrical sense. Okay. What else? Okay. Linear space. Two vectors are dependent if one linearly dependent, especially linearly dependent when one is a scalar multiplication of the other. Okay. When two vectors are not linearly dependent, they are linearly independent. Here, what you have to be careful about is to distinguish linear dependence from linear independence from statistical independence. So later, you probably know already about the statistical independence. Statistical independence doesn't mean linear independence. Okay, so there are two different concepts of independence. So don't get confused. Since my course is linear econometrics, which is based upon the statistics. When I say independence, it usually means statistical independence because we usually are dealing with random variables. Okay. But for now, we are talking about deterministic vectors, not random vectors, and we are talking about linear independence, not statistical independence. Two vectors u and v both are not zero vectors. They are linearly independent if they are not linearly dependent. If two vectors u and v are linearly independent, then it means you cannot combine these two vectors linearly, meaning that you cannot find out alpha and beta that are not zero at the same time. That makes alpha u plus beta v equals to 0, the zero vector. Here, this is the zero vector. Okay, that's what linear independence means. Orthogonal, two vectors are orthogonal if their inner product is 0. Okay. You can define an angle. The angle between two vectors is the inner product divided by norms of the two vectors. That's gonna be the cosine value of the angle between two vectors. Okay. Geometrically, suppose this is your vector and this is your u vector and v vector, in whichever dimension. Let's suppose this is a two-dimensional vector. Then the angle is defined. Angle is defined this way. Okay. And this also is u over u and v over v. So this is normalized u and this is normalized v. So the inner product of normalized vectors is the angle between two vectors. Okay. Now consider a two-dimensional Euclidean space here, which means that two-dimensional Cartesian product here of R's. So this is your R2. And a linear space is a space, a subspace, or a subvector of this two-dimensional R2 that satisfy these two conditions. Okay. So let's think about this. Can this be a linear subspace? So let's call this one L1. Okay. All right. Let's see. The first condition is if y is in L, then x plus y is in L2. So this is x, this is y, this is vector x, and this is vector y. If you add vector x and vector y, you get somewhere in here. So this is your x plus y. So L1 satisfies this condition. What about L2? If x is L1, then alpha, and alpha is a scalar, then alpha times L is L1. Right? So x is L, and this is 2. This is alpha x. So whichever alpha is, whatever alpha is, alpha times x is in L1. So this L1 satisfies this second condition too. Therefore, L1 is a linear space, linear subspace. What about this whole thing itself, R squared? Is it a linear subspace? Of course. Well, then what space is not a linear subspace? Consider this space. Okay. So this is L2. Okay. Mathematically, L2 is so suppose this is B, okay, and this is A, this is 0, B, this is A, 0, okay. Then L2 is a set of x, y values such that y is b plus a over b x minus, okay, minus b over a x. Okay, so if your x is 0, then your y is b. If your x is minus a, if your x is a, then y is 0. Yes, that's your L2. So is L2 a linear subspace of R2? It turned out no, because consider this vector x. Here's vector x, and here's vector y. Then vector x and vector y is here. Okay, sum of these two is here. So x plus y, both x and y are members of L2, but the sum of x and y is not a member of L2. Right? So the first condition is violated. The second condition is violated too, because if this is x and let's make twice the vector x, then 2 times x is here and it's not in L2. So this subspace is not a linear subspace. So what you can think is, what you can understand is, a linear subspace must contain the origin. So 0, 0 must be in the linear subspace. Okay. Now, let's get back to our linear subspace here. So this is your R2 and this is your linear subspace. Here L1, what is L1? L1 can be written in various ways, but consider one vector here, This is your vector x. X is 1 and 1/2, or 2, 1. Let's say 2, 1. X is, oops. Two, 1. Then L1 is set of say x1 and x2 such that x1 and x2 is alpha times 2, 1. Okay. So we say the L1 is spanned by 2, 1 vector. So this 2, 1, a linear combination of this 2, 1 generates this whole space L1. Okay. This also spans L1. So L1, now think about x and y 4, 2. Then L1 is a function x1, x2 such that, let's use boldface here, x boldface and y boldface to denote that they are vectors. Alpha x plus beta y is x1 y the x2 for some alpha and beta, right, scalars. So L1 also both x and y span L1 as well. What about this? What about this is the R2 and you have two vectors here. This is your vector x and this is your vector y. Excuse me. And this is your vector y. And what is the linear subspace that both x and y span? It's a line, right? It's a line. It's the L1 basically. However, if your y is here, suppose this is your y. This is your y. Then you can show that every point in R2 can be written as a sum of these two, linear combination of these two. For example, here, this point. Oops. Say this point. Okay, so find out a way that, let's say this is your z. Your z is, find some alpha. I'm claiming that alpha times x plus beta times y for some alpha not 0, some alpha and beta. Okay, so find out how you find alpha and beta in this example. Here, since zeta, you can find for any value, for any point in R2, there is linear combination coefficient alpha and beta that gives you that point for x, for a linear combination of x and y. The whole space R2 is spanned by x and y vector. Okay. All right. Now, there's this concept of basis. The R2, the whole, this x vector and y vector span the whole R2 space. So, the vector, the set of x, the x and y constitute the basis of this R2. Okay, basis is not unique. This can be a basis, as well as z and x can be as well. Okay, but so your x and y is a basis, x and z is a basis, but x, y, z is not a basis because they are linearly dependent. How do you know that they are linearly dependent? Because z can be written as a linear combination of alpha of x and y, which I want you to prove. So this is a basis for R2 space, this is a basis for R2 space, but this is not a basis for R2 space. So R2 space is two-dimensional. You may think it's obvious, but actually the dimension of a space is defined by the number of vectors in a basis. So here you have two vectors. This is not the basis. So however you form the basis for R2, you always have two vectors in the basis. So the dimensionality of R2 is 2. What about this? What about this linear subspace? Oops. What about L3? Then L3 can be written as a linear combination of this vector, one vector. So it's a one-dimensional linear space, two-dimensional linear space, three-dimensional linear space. Think about a plane in a three-dimensional space, three-dimensional Euclidean space. This is a Euclidean space, and this is a plane. Okay, and so let's draw a graph a little bit clearer. So here's Euclidean space, not restricted on this plane, so it cuts through this space in this way. Okay, so is this a two-dimensional linear space? Answer: no, it's not a two-dimensional linear space. It's a two-dimensional space in three-dimensional space. So it's a two-dimensional subspace in three-dimensional space, but it's not linear because it doesn't cut through the origin. The origin is not included in this space. Okay. All right, two linear spaces L1 and L2 are linearly independent. Now we are talking about linear independence of spaces. What do I mean by linear independence of spaces? Here, this space is linearly independent of this space, this subspace L4. How do we know that? Because every point in here in L4 cannot be generated. Any point in L4 cannot be generated by any combination of L3 of vectors in L3. Okay. Sorry, I think I need to back up. Here, I meant so two linear subspaces are linearly independent or orthogonal to each other if vectors in two spaces are orthogonal. Here, so L3 and L4 are orthogonal. Right? L3 and L4 are orthogonal linear subspaces. Okay. Now think about this case. So here x1, x2, x3 are three-dimensional vectors, y as well. Okay. And theta 1, theta 2, theta 3, every single of them is scalar. So in combination, it forms a three-dimensional vector space, a three-dimensional vector. Okay, consider this space that this is true. You can rewrite this way, and this is something similar to a linear combination, a linear regression model that you are going to see soon. Okay. And What else? Okay, why do we do this? Okay, here an important concept here is the concept of rank. So we already know that a set of linear combination, linear equation system, a system of linear equations can be written as this this matrix form. And this is a coefficient matrix, this is a variable matrix, this is a just constant vector, variable vector, constant vector. And the rank of coefficient matrix is the number of linearly independent columns in X. Here, if x1, x2, x3 are linearly independent, then the rank of X is in this case 3. Okay. Yeah. If x1, x2, and x3 are not linearly independent, suppose your x3 is linear combination of x1 and x2, and there's only x1 and x2 are only x1 and x2 are linearly independent, then the rank of X, although it has 3 columns in it, the rank of X is 2. When the column rank, the number of columns and the rank are different, are the same, is called the full rank. So here, yeah, it's called the X has full rank. Okay. Rank has the following properties. And when you solve a non-stochastic linear equation, then rank conditions, this part gives you the idea whether the system has a solution or not. In econometrics, however, the system, the situation is a bit different, because in econometrics, what you have is this. Here you have response variable vector. Here you have control variable matrix. Here you have coefficient vector. And here you have unknown, unobserved error term vector. We are going to come back to this point later. So the rank condition doesn't necessarily imply the existence or the uniqueness of the solution of theta in this case. You need to think a little bit more carefully. But understanding of these conditions will give you a basis for understanding of linear regression later. And the understanding of concept of rank is important. Okay. So corner space and column space. Okay, do the exercise problems here from E. Read the things carefully and do this. And get an understanding of column space especially, okay, of a matrix. So eventually what this is related, how this is the concept column space and so on and so forth are related with is this. So the linear regression model is this. Suppose you have k control variables, then and this is your first observation, and this is your nth observation, first observation. So this matrix notation is a matrix form of the following linear regression model. So yi equals to x1i beta 1 plus x2i beta 2 plus plus xki beta k plus epsilon I. And suppose you did a regression and you obtain the OLS estimate beta hat. So here you have this, and you have residual here. Okay, so your y can be written as this part and residual part. Okay, and the way you obtain beta hat is minimizing this one. So this is what? This is your residual. If you plug in this is your residual as a function of beta. Sorry. So okay, now let's define residual epsilon as a function of beta by y minus x beta. Then this is residual times residual, so it's the sum of squared residuals. So you are minimizing sum of squared residuals. The minimizer is called beta hat. So beta hat, the first order condition of this minimization problem is this. The first order condition of this minimization problem has to be this partial beta y minus x beta prime y minus x beta, which is partial beta y prime y minus beta prime xy minus y prime x beta minus beta prime x beta. here y prime I doesn't have any beta, so it doesn't. It's just a shifting parameter of the objective function, so you can ignore this part, right? So this is the first order. You set this to be 0. Okay, so your beta hat must satisfy this, right? Then when you do the matrix differentiation, you get this. You get x prime y minus x beta hat equals to 0 at the first order condition, and that gives you this. So if you define y hat by this, okay, and let's call this matrix P sub x, and this matrix M sub x, then your y hat is in column space of P sub x, because y hat is P sub x times some value y, right? And epsilon hat is a column space of M of x, because epsilon hat is M sub x times y, by definition of column space. And we will see that the rank of P sub x is the same with the rank of x. And here x is k, and the dimension of this one is n. So the rank of x is smaller than the row dimension. So P sub x, what is the dimensionality of P sub x? P sub x is, if you think, here x is n by k, so here you have n by k, and x prime x is k by k, inverse is k by k, and x prime is k by n. So in total, P sub x is n by n matrix, right? It's a square matrix of dimension n. But the rank of P sub x is smaller than n. It's actually the rank of x, which is in this case k. And so the P sub x divide the n-dimensional Euclidean space into two. It forms a linear subspace in n-dimensional Euclidean space. Precisely speaking, it constructs a k-dimensional linear subspace in n-dimensional Euclidean space, and the M of x also constructs a n minus k dimensional linear subspace in n-dimensional space, Euclidean space. Okay. So we are going to learn this part, and to learn this, you want to have pretty good understanding of the concept of column space and rank and so on. Okay. All right. And the next topic is projection. Graphically, I think graphically, it's better for you to approach to the idea of projection graphically or geometrically. Is this? Consider a three-dimensional. Suppose your n is has 3. So y is r in R3. So y is a three-dimensional vector. Suppose this is your here's a three-dimensional vector y. This is your y. Okay, this is your y. This is your y. And P is a matrix. Let's say your K is 2. So P is a matrix R2 by 3. Okay. Okay, so consider the following problem. Y is in R3, and you are going to do the following projection. So consider a span of 1, 1, 1 and x1, x2, x3. So I'm gonna call this iota 3, and I'm gonna call this x. Okay. Now, the span of these two vectors is, so here's your iota 3, and here's your x, then a space generated by this linear combination of these two is the span, right? This is the span of iota 3 and x, right? And so think about a vector y. Y is here. This is your y. Okay, and iota 3 and x forms a two-dimensional Euclidean, two-dimensional linear. Suppose two-dimensional a linear space. Okay, for simplicity. Then consider a projection of y onto this space. Okay, y onto this space. So the projection of y onto this space, I'm going to call this y hat, is this y hat. Okay, and by definition, your y hat is a linear combination of iota 3 and x. So your y hat is linear combination of iota 3 and x. So let's put this linear combination coefficient as beta 0 iota 3 plus beta 1 x. Okay, or simply put iota 3 x and beta 0 beta 1. Okay, even simpler, I'm gonna call this thing x. X is iota 3 x, that's your x, and I'm gonna call beta 0 and beta 1 this two-dimensional vector beta. Okay, and then let's put hats here. So this is your beta 1 hat x, and this part is your beta 0 hat iota 3. So your y hat is this. So here's your hat. So your y hat is x times beta hat. Okay. All right. What is this vector then? This one. So your y hat is let's call this epsilon hat. Okay, epsilon hat. Then your y is y hat plus epsilon hat. Both y hat and epsilon hat are three-dimensional vectors. And because y hat resides in this plane, and epsilon hat is orthogonal to this plane here, epsilon hat can be computed by epsilon hat must satisfy the following: y hat, y minus y hat, and the norm is minimized, right? So consider a non-projection vector so consider a vector this, and this is not a projection vector because and this is not a projection vector, and the fact that this is not a projection vector implies that this length is greater than this length, right? The y hat length of epsilon hat. So in fact, when your y hat is a projection of y onto this space, the length of this vector y minus y hat is minimized. So the way you find the projection vector is minimizing the length of this one. So the way you find projection vector, by the way, what is the projection vector here? This is your projection vector. So the way you find this projection vector coefficient is you minimize y minus x dot beta hat. You are going to minimize the norm of this one. Minimization of this norm is basically minimization of this one, right? Which is the OLS. So the OLS is to find basically the projection vector of your y, right? And we know what beta hat is. Your beta hat is x prime x inverse x. Therefore y hat is y hat is x prime x inverse x prime y, and this is our piece of x in the previous notation, piece of y. So y hat is in column space of P of x, right? So here the thing that we have in mind is this P matrix is this Px matrix. So the projection vector yp, actually in our notation y hat. So here y hat is the projection of y onto the column space of P of x, which is the span of iota 3 and x. Okay, so this is what we have in mind when we are doing this projection. And projection means y and y minus y hat is orthogonal, right? That's what a projection means. So this is your y, and y is projected onto the space of iota and x, and this is your yp or y hat. So the projected value, this y hat, projected value y hat is orthogonal to y minus y hat. Okay, all right. Since this is orthogonal, y hat prime y minus y hat is 0. And what is our y hat? Y hat is x prime x beta. So y hat is what? Beta hat prime x prime, and y is y minus x beta hat, and this has to be 0. Okay, so this is 0 when this is 0, So from this being 0, we get beta hat is x prime x inverse x prime y, right? Okay, so that's this. And this section gives you a general understanding of the concepts and properties of projection here. So So read this part carefully. And what you can think is this. Here, this is again y, and this is the space, the span by iota 3 and x in our example, which is the column space of P of x, okay, where P of x is x prime x inverse x prime, okay, and this is y hat, or the projection of y, and this is the residual, what we call, okay, and so y hat is P of x times y. Now let's do the projection again. So P of x y hat, so twice the projection, okay. So if you project y hat again onto itself, it is the same because it's already there, right? So it is P of this is y hat, this is y hat, and what is P x of y? P x of y is P of x times P of x y,
처리 중입니다.
which is P of x squared y, and what is y hat? That's P of x y, therefore P of x squared is P of x, okay. So projection matrix is symmetric and idempotent, and geometrically it has to be because of this property, okay. Right. Okay, so read this part carefully. Now we are going to talk about eigenvalues. What is eigenvalue? Eigenvalue. I didn't define the eigenvalue. An eigenvector of a square matrix is a scalar lambda and vector v that satisfies the following. Okay, so a square matrix A, this is a square matrix A, and this is a vector v, is lambda times vector v, okay. So if you find lambda and v that satisfy this, it's called the eigenvalue and eigenvector, okay. Example. Suppose your A is 1, 2, 1. Find an eigenvalue. Okay. There is a systematic way of doing eigenvalue thing. The way you do is this. Bring this to the left hand side. Then this matrix equation becomes something like this: A minus lambda identity times V is 0. Okay. From here, you get this condition, determinant of A minus lambda identity is 0. This is called the characteristic equation. Characteristic equation. In the previous example, suppose your A is 2, 1, 1, 2. Then the characteristic equation becomes 2, 1, 1, 2 minus lambda 0, 0, lambda, and determinant of this is determinant of 2 minus lambda 1 and 1 2 minus lambda, right? And we know how to do the determinant for a 2 by 2 matrix. It's gonna be 2 minus lambda squared minus 1. That's the determinant, and it has to be 0, right? It has to be 0. So we have two solutions: 2 minus lambda minus 1 and 2 minus lambda plus 1 is 0. So the lambda, there are two solutions. Lambda is either 1 or 3. Right? Okay. So when lambda is 3, when lambda is 1, we have this 2, 1, 1, 2, and v1, v2. That's the vector v is v1, v2. That's for lambda is 1. For lambda is 3, we have 2, 1, 1, 2. v1, v2 is 3, v1, 3, v2. From this, we get 2 v1 plus v2 is v1, and v1 plus v2 is 2v2 is v2. So you get this v2 equals minus v1. Right? So v1, v2 has to satisfy this one. So it's of the form, for lambda 1, it has this form 1 minus 1 to some value k. Okay, so for lambda is 1, we have k 곱하기 k times 1 and minus 1. For lambda is 3, we have v1, v2 is k times 1 and minus 1. For lambda is 3, here we have this, and 2 v1 plus v2 is 3 v1, and v1 plus 2 v2 is 3 v2. So v1 is v2, right? v1 is v2. So for this one, v1, v2 is k times 1 and 1. We want to normalize the vectors. So the normalized vector here is 1 over square root 2 minus 1 over square root 2, 1 over square root 2, 1 over square root 2. Okay, so after normalization, we have two eigenvalues. Lambda 1 is 1, and the associated eigenvector v1 is 1 over square root 2 minus 1 over square root 2, and lambda 2 is 3, and the associated eigenvector v2 is 1 over square root 2, 1 over square root 2. Okay, that's how you find out eigenvalues and eigenvectors. Alright, I want you to do exercise about eigenvalue, finding eigenvalues and eigenvectors. There are properties that eigenvalues and eigenvectors have. First one is this: a symmetric matrix. So if a regular matrix is symmetric, then eigenvalues are real. It means if they are not symmetric, eigenvalues may be complex. Yes, indeed. A symmetric matrix is singular if the minimum value of eigenvalues is 0, if and only if. So, in this case, the A matrix was 2, 1, 1, 2, and none of these two eigenvalues are 0, so it's not singular. You can invert the value, the matrix A. If A is symmetric, then the rank of A is the number of non-zero eigenvalues. Okay, all right. Let's do the exercise. No, I will let you do. The exercise. Okay, think about this. 3, 1, 1, 1, 3, 1, and 1, 1, 1. Oops. And let's say 0, 0, 0, 0, 0, 0, 0. Okay, this is your A, and they are symmetric. The A is symmetric, so the eigenvalues has to be real. It's not a full rank, actually. The rank of A is 2, as you can see. So what you can expect is you can find out, you can compute, you can see that the eigenvalues of A are real, and there will be 3 eigenvalues, and one of them is 0. Okay. So compute the eigenvalues. Alright, if A is symmetric, then eigenvectors are orthogonal to each other. In the previous example, eigenvectors were 1 over square root 2, 1 over square root 2 minus, and 1 over square root 2, 1 over square root 2. A was symmetric, so let's see if these are orthogonal vectors. The inner product of this is 0, so orthogonal. That's true. Okay. The trace of A is sum of eigenvalues. Eigenvalue was 1 and 3, and A was 2, 1, 1, 2. So the trace is the sum of diagonal elements. As you can see, the trace of diagonal elements, the trace of A is the sum of sum of eigenvalues. Determinant of A is the product of eigenvalues. So here, our eigenvalues were 1 and 3. Determinant is 4 minus 1, which is 3. So, verified. Okay. So we are going to learn the special matrices such as positive definite, positive semi-definite. Okay. If the matrix A is idempotent, then what we know is eigenvalues are 0 or 1. And it's not easy to prove. It's related with what is called the spectral decomposition theorem, or we also call it eigenvalue decomposition theorem. So spectral decomposition and eigenvalue decomposition are, at least in our context, identical. Okay, consider a symmetric matrix A. Then A can be diagonalized in the following way. So A can be written as P times a diagonal matrix lambda times P prime when A is symmetric. Okay, so this is the proof, and read this proof, follow this carefully, and do the exercise problems. Okay, do the exercise problems. So I guess let's leave the remaining topics for the next lecture. So take a break.